Okay, so today we will solve GET 2023 questions from complex analysis. This is question number 27. It is saying that let z by 1 minus z minus z square. This is analytic function is given, and it has written in terms of this power series in some neighborhood of 0. Right, you have to find the value of a6 and a5. So the coefficient of the power series means 6, a6 and a5. Okay, so we have to find the value of this. So in order to solving this is the NPTEL reference. You can look into it. Okay, so this can be solved means you just take the polynomial and there is a formula for some nth coefficients, but we will solve some other way. There is a, so let's see. Note that the function what is given, so fz, what is fz? Let's say z by 1 minus z square. So it has written in terms of this power series. Right, so this you can solve by this, but one can prefer if one can view that this denominator, so this is basically means if you write it 1 by 1 minus z square, this is basically the generating function for the Fibonacci sequence. So if one can see it easily, then the problem will be easier to solve. So let's do this. So this will be the generating function. Or Fibonacci sequence. Okay, so what is this Fibonacci sequence? Suppose this B0, this is 1, B1 to B1. Now what will be the second term? It will be just add the previous two terms. So it is 2. B3, what will be the add the previous two term? 3. B4, add to previous two term 5. B5 basically add previous two term 8. What will be B6, add previous two term 13, and so on, right? So what is the general formula? So Bn, you can write Bn minus 1 plus Bn minus 2, means just add the previous two terms. So this is the recurrence relation for Fibonacci sequence. Right, so we will show that this is the generating function for this Fibonacci sequence. So what is mean by this? So suppose means generating function means we can write this 1 means 1 minus z square. We want to write is as some bn z to the power n equals to 0 to infinity, where these bn's are Fibonacci sequence we want to write, right? Where bn are as above. So let's first prove this. So let fz to be this, take this series bn z to the power n. So this is the formal power series. How you can write? So take out the first two terms, because this is a recurrence relation for n bigger than equals to 2, so you will use this. So first term is b0 is 1, and what is b1? So it is z basically, right? b1 is again 1, and now you can write n equals to 2 to infinity bn z to the power n. Now put this recurrence relation here. So if you put this, what you will get? It will get bn minus 1 plus bn minus 2 z to the power n. Right, now separate it out. 1 plus 1 by z, n equals to 2 to infinity bn minus 1 z to the power n plus summation n equals to 2 to infinity bn minus 2 z to the power n. Now what we will do here, we will make change of variable, that n goes to n plus 1, and for the next one we will make change of variable, n goes to n plus 2. So then 1 plus z, it will become n equals to 1 to infinity, means this is same bn z to the power n plus 1 plus n equals to 0 to infinity bn z to the power n plus 2, right? Therefore this you can write, take the z common from this one, so this is basically n equals to 1 to infinity bn z to the power n plus, take z square common, it is n equals to 0 to infinity bn z to the power n. Now look, this is the sum from n equals to 1 to infinity, right? But here it is sum from 0 to infinity, but here n. So we will just subtract the first term and write sum from 0 to infinity. What is the first term? First term b0, which is 1. So that's why we can write this as sum from n equals to 0 to infinity b0 z to the power n minus 1 plus z square. This is the as it is, because this is the it is sum from n equals to 0 to infinity, right? And we have denoted this by fz, this sum. So therefore what we have, 1 plus z plus z, this is fz minus 1 plus z square fz, right? So if you simplify this, what you will get, 1 plus z fz plus z square fz. So fz equals to, we have got this. So now take all the f in one side. So therefore fz equals to 1 plus z fz plus z square fz. Now take fz in one side. So fz, if you take, what you will get, 1 minus z square equals to 1, or fz is what we have got, 1 by 1 minus z square. So what we have seen, that this series is basically this analytic function, right? So this, so therefore that we have to here. So 1 by 1 minus z square. So this is basically this, n equals to 0 to infinity bn z to the power n, where what is bn? This is the Fibonacci sequence, where b0 is 1, b1 is 1, and bn is Fibonacci sequence bn minus 1 plus bn minus 2 for n greater than equals to 2. But we have the function z by 1 minus z square. So just multiply by z. Therefore z by 1 minus z square, it will become n equals to 0 to infinity bn z to the power n plus 1. And it is again given that this sum is equal to, they have given this power series. Now we have to find the value of a6 and a5, right? So let's write So this is also same as this, n equals to 0 to infinity an z to the power n. So if you compare these two, so comparing, what we will get? So this, if we compare this to, what we will get? Bn equals to basically an plus 1, right? Because it is here z to the power n plus 1, here it is z to the power n. So for all n, right? Yeah. Then what will be this? Then what is a6 plus a5? So a6 plus a5 means b5 plus b4. And what is b5 plus b4? So means what is the fifth term and fourth term for the Fibonacci sequence? So that we have already written it down, right? Fifth term is 8 and fourth term is 5. So this will be basically 8 plus 5. It will be 8 plus 5. So it is 13. Therefore a6 plus a5 is 13. So therefore what is this? This is 13. Okay.